Hi, welcome to this video on linear programming duality. This is the follow-up to the previous video in which we were discussing how to take the dual of a linear program directly. And so this will rely on that video for context. And in that video, we had these two linear programs which appeared, this one on top and this one on bottom, and we had claimed that they were in fact equivalent to each other. But we did not justify this claim at the time. So this was a tangential side point that we made at the time. The real main point we were making is how to directly take the dual. And we claimed that when we did so correctly because we were supposed to end up with these two linear programs being the same. So we just said that they were. So now we will actually show that in fact they are. So that's the purpose of this video, to show the equivalence of these two linear programs. Okay, and so it should not be surprising if you recall where these linear programs came from, that in fact they are equivalent to each other because they were derived by taking the dual of the same linear program in two different ways. What happened was that we had an initial linear program, a primal, and we took the dual of it in two different ways. The first way was by reformulating it so that all of the constraints were of a uniform type, and then we took the dual. And that gave rise to this linear program here on bottom, where again, you can see all the constraints are of a uniform type. We have matrix equality constraints and variable non-negativity constraints. And then in the most recent video, what we did was we took the dual of that same linear program, but instead of first reformulating it, we simply took the dual directly, and that gave rise to this linear program here. And since all the constraints were kind of mixed and matched in the primal, they also are in the dual as well. So we have all sorts of hybrid constraints here in the dual. But since we took the dual in two different ways, it should make sense that it's still the same linear program, just reformulated, because what we did with the primal was we either reformulated it or we didn't, and then we took the dual. So now we should just be able to have these two different duals. They should be reformulations of each other as well, and in fact they are. So we'll see how that works. And so what we're going to do now is we're going to start with this linear program here on top, and we're going to reformulate it so that it is of the form on bottom. So let's see how that works. Okay, so here's the linear program again, and before we go out of view of this linear program on bottom here, let's just know we have matrix equality constraints and variable non-negativity constraints, and so what that means is that's what we want for this linear program here now. So we want these constraints to become matrix equality constraints, and these variable constraints to be variable non-negativity constraints. So let's start with the variables. So we want the variables to all be non-negative, and so what we'll do is we'll specifically start with y1 then. So we'll just do things one at a time. And so there's just standard techniques involved in rewriting things so that you get the format that you want. So we want all non-negative variables. There's a technique for doing that. So we start with y1 here, and y1 is less than or equal to 0. And so what you do then is you introduce a new variable, v1, and that'll be equal to minus y1, which will be greater than or equal to 0. And so the idea is that you want to replace y1 with v1. But you can't just arbitrarily replace this because that's going to fundamentally change the linear program. And we're not looking to do any fundamental changes. We simply want to perform artificial changes, which only change the format, but not the underlying linear program. So we can't just do this replacement. What we have to do is be just slightly more clever. We have to, since what we're going to do is we will end up replacing y1 with v1, that's going to introduce a minus sign to all the places where y1 used to appear. Now there's going to be an extra minus sign. So where did y1 used to appear? Well, it used to appear here in the objective function as the first entry, after that coefficient there, and then same thing for these coefficients in the first column. Those are the coefficients that are associated to the variable y1, so both in the objective function and in the constraints. And so what we're going to do then is we're going to manually insert a minus sign in front of all those coefficients. That way, those coefficients being multiplied by minus y1, we'll have two minus signs that'll then cancel out with each other, and so then nothing will have fundamentally changed. The difference now will be that we're expressing the linear program in terms of v1, which is now a non-negative variable. So what we do is we take this coefficient here, this minus 2, and we're going to change it to a plus 2. And then for these coefficients in the first column, they become a -1, -2, and -1. And now we can replace y1 with v1. So that's how you take care of that. You just negate everything in the first column. Okay, and well, then for the second variable, you see that it's already a non-negative variable. y2 is greater than or equal to 0 already, so v2 will equal y2. You don't change anything. It's because y2 is already non-negative. So v2 is the same thing. We don't even need to call y2 v2. It's just that for consistency's sake, we're going to replace the y's with the v's. And so all the new variables will be called v's, just for consistency. So v2 is the same thing as y2. It's just a relabeling because it was already non-negative from the start. Finally, we have y3, which is a free variable. And so the technique for replacing free variables with non-negative variables is to note that any number can be written as the difference of two non-negative numbers. So that number can be positive or negative. No matter what it is, I can write it as the difference of two non-negative numbers. And so that's easy to see. So then what that means is that we can replace a free variable with the difference of two non-negative variables. So y3, a free variable, we will replace it as a v3 plus minus v3 minus. So that is the difference of two non-negative variables. So v3 plus and v3 minus are both going to be two new variables, and they will both be non-negative. So we have two variables here that are replacing the single variable y3. And so now you can see all our variables are of the correct form. They're all greater than or equal to 0. So let's just see how we can rewrite, for instance, the objective function in terms of these new variables. What we'll have is we will have, we're going to have 2, so now positive 2 there, v1 plus 2v2 plus 13 times v3 plus minus v3 minus. So we can just distribute that, so 2v1 plus 2v2 plus 13 v3 plus minus 13 v3 minus. And so the point is that what's going to happen in general, not just for this function in terms of the variables, but also in terms of the constraints, is that so the first coefficient gets negated, as we already said. The second coefficient remains as it was before, it doesn't change, and then we're going to have two copies of the third coefficient because you see here, so for this third column here, both for the objective function component and for the matrix constraints, everything in that third column, it's going to get copied. There's going to be two of those coefficients appearing now, one with a plus sign and one with a minus sign, because one will be associated to the variable v3 plus, and then one will be subtracted off because of v3 minus. That's the one that's being subtracted. So we'll have a minus sign in front of the final variable there. Okay, so what does that mean in terms of, we can also write down the matrix constraints. So what does that mean? How do we do that? Well, we already said we negate the first column, so -1, -2, and -1. The second column stays intact, so 4, 6, and 5. So that's because the second variable didn't change. And then for the third variable, it was replaced with two new variables. So we'll have two new columns, one with a plus sign, one with a minus, because one's v3 plus has a positive, it's positive, and then v3 minus, it's still non-negative, but it's being subtracted off, so there's a minus sign in front of it. So so what we'll have is 2 minus 1 minus 3. That's just copying that over. And then we'll have minus 2 plus 1 plus 3. So that's negating it for the v3 minus variable. So this matrix, and then times the variables. So the variables are v1, v2, v3 plus, and v3 minus. And so those are the variables now, and the constraints still haven't changed. The matrix constraints are still greater than or equal to, and greater than or equal to. And so, and the right-hand sides also are the same as before, 12, 26, and 20. So that's how you rewrite the matrix constraints in terms of these new variables. And the difference now is the variable constraints are now all non-negative. So v1, v2, v3 plus, and v3 minus are all greater than or equal to 0. And that is what we wanted. So that's how you rewrite it with non-negative variables. Okay, and so this is just that cleaned up. So the objective function, you can see there in terms of those new variables, and now all the variables are non-negative. Okay, so now what we have to deal with is we have to deal with these constraints, the matrix constraints. Okay, so let me erase the part for the variables because we're going to focus on the constraints now. Matrix constraints. What we have specifically is you can see that the first and third constraints are the ones that are not equality constraints, and that's what we want. We want equality constraints. So we're going to have to do a replacement there. And so there's a standard technique again for doing such a replacement of constraints like that. What you do is you add on a new variable again, but this time it's not for the sake of renaming variables for non-negativity constraints. That's not the purpose. The purpose is to change the matrix constraint. So let's just write down the constraint. Let's focus on this top constraint here. So let's write that down more explicitly. This is minus v1 plus 4v2 plus 2v3 plus minus 2v3 minus. That is greater than or equal to 12. So we want this to be equal to 12. But whatever this left-hand side is, we don't know what it is, but it's larger than 12. It's no less than 12. So what you do is you add on a surplus variable. So a surplus variable is just, I should say subtract off a surplus variable. A surplus variable is going to be, so you know the left-hand side is larger than 12. Whatever amount larger at 12 than was, that's the amount that gets put into the surplus variable. So what we're going to do is rewrite this. So this becomes minus v1 plus 4v2 plus 2v3 plus minus 2v3 minus, and now plus, I'm going to call it S1, S for surplus, and this will be equal 12, okay? And the idea is that the S1 will be greater than or equal to 0. We want all our variables to be greater than or equal to 0. And, oh, and by the way, this isn't a plus sign, this is a minus sign, because we're subtracting a non-negative amount off. Because originally what we had was, we had this part right here up until the surplus variable, and that was larger than 12. And now we're going to subtract off a non-negative amount in terms of the surplus variable. That's what's going to drag us down to equal 12 exactly. So you always would choose the value in S1 to be whatever extra amount you had, the surplus. And so anyway, so that new variable gets introduced so that we can now have an equality constraint. And then the same technique is applied for the third constraint as well. So we have this third constraint here, and I'll just directly write the new constraint that we're going to have. It'll be minus v1 plus 5v2 minus 3v3 plus 3v3 minus, and then minus s2. So s2 is a second surplus variable, and that will equal 20. So again, s2 will be a non-negative variable. So it's some non-negative amount that we're subtracting off, corresponding to however much overboard the initial left-hand side was. It was more than 20, so whatever extra amount we had, that amount gets put into S2 and subtracted off so that it now equals 20. Okay, and so with those constraints written now, we can now rewrite the linear program one more time. And so here it is. What we have, you can see, is here is the objective function now, and it's expressed in terms of all the variables. That's fine as is. I'll come back to it in just a moment. But specifically, let me draw your attention to the constraints now. The constraints are now all equality constraints, which is what we wanted. And the variables, again, are still all non-negative variables. That's including the two new surplus variables that we've now included as well. So everything's expressed in terms of all 6 variables that we have now. And And so you can see for these constraints here, what happened is we have these two new columns. So these two new columns here came from the fact that so this -1 was when we're subtracting off S1 for the first constraint, and then this -1 is we're subtracting off S2 in the third constraint. And so that's where they come from, and that's why those columns are now there. And then for the objective function, we have zeros for these final two coefficients, because that's corresponding to the fact that we are not expressing the objective function with the surplus variables. They don't get factored into the objective function at all. So there's zeros corresponding to those variables there. So okay, so that is how you can rewrite this, and now everything is how we want it. We wanted to have matrix equality constraints and variable non-negativity constraints, and that is what we have. And the final thing to note is that there is no reason to have all these weirdly named variables in terms of V's and S's and pluses and minuses. None of that's necessary. We can just relabel things. Let's call everything Y's instead of V's and S's and stuff. And so we can write it like this instead, where Y, it's the vector. So Y is, of course, it's Y1, Y2, Y3, Y4, Y5, Y6. So 6 components, just like there's 6 components before. We're just relabeling them again, calling them Y's just for consistency's sake. And there you go. And so this is the formulation that was what we wanted to achieve. So we've just achieved it. So in conclusion, what did we just show? We just showed that these two linear programs here on the left and right are equivalent to each other. And so that means that that when we took the dual in two different ways, it's okay. It doesn't matter how you reformulate the linear program. When you take the dual, it's just going to give you some equivalent version of the dual. All the duals will also be equivalent to each other up to some reformulation, as long as the initial primals were equivalent to each other up to some reformulation. So primals and duals really do come just in pairs with each other. You can't get different types of things in that way. Just as a final note, what does it actually mean to be equivalent? I mean, they're not literally the same linear program, because just at face value, they're different coefficients and everything. They're not the same linear program, but there is a correspondence between them, and that correspondence is what we're calling equivalent. So what does that actually mean? Well, it means that there's just a well-understood way to map between the solutions, and that those solutions, in fact, when you plug them into the objective functions, give you the same values as well. So just for example, what we mean is, well, let's take, for example, a solution y bar for this right-hand formulation of the linear program. We had, in a few videos ago, we had that y bar being 0, 4, 0, 2, 0, 0, that was a feasible solution. And we were discussing weak duality at the time, and so by weak duality, not only was this a feasible solution, but we showed that it was an optimal solution. It came as a primal dual pair of optimal solutions, as shown by weak duality. So what does this mean in terms of the formulation on the left, then? How does this solution map to the left? First of all, let me just note that the objective function, when you plug this y bar in, the objective came out to be -18. So we were trying to minimize, and so an optimal value, a minimal value for this linear program was -18, as achieved by this solution y bar. So what does this get? Since they're equivalent, I should know an equivalent vector in the left-hand formulation of the linear program. So what is it? Well, let's just remember for these components, these are the 6 components here. So this is V1, V2, V3 plus, V3 minus, S1, and S2. That's where they came from. And the reason that we generated those variables was so that they were all non-negative. But what do they correspond to? Well, okay, so let's write down we'll call it y tilde for the left hand here. So it's 3 components. So the first component is going to be the negation of v1. Remember, v1 was that we negated the original y1 variable, since here on the left, y1 was less than or equal to 0, so by negating it, it became greater than or equal to 0, and that's what v1 was. So this is minus 0 for the first component, which of course is still 0, but anyways, so then the second component was 4. That did not change. y2 was v2. So we have a 4 here. And by the way, when I'm saying the y's here, of course, are not the same thing as the y's here in terms of components. It's just the notation that we're using associated to the name of the vector. So when I'm saying y2 here, I'm talking about that component y2. Okay, anyway, so minus 0, then 4, and then finally for the third component, what we had was, it was the difference of, so we had these two variables on the right here, v3 plus and v3 minus, and it was the difference of those two that gave rise to the free variable y3. So the difference then is 0 minus 2. And then the surplus variables played no role in terms of expressing the components of the left-hand side. So this becomes then 0, 4, minus 2. And so that's the correspondence. And so it's not just with this solution, but for any solution to the right-hand formulation, there's a corresponding solution to the left-hand formulation, and vice versa. We could have started with 0, 4, minus 2, and then on the right-hand formulation, we would have achieved 0, 4, 0, 2, 0, 0 by just doing the logic in reverse. So that's the correspondence. And by the way, you can see that when you plug in this into the objective function, the objective evaluates again to minus 18, as it should, corresponding to the fact that that's what we mean when we're saying linear programs are equivalent. So so it's just, there's a correspondence of the solutions, so that the objective functions, when you plug those corresponding solutions in, give you the same values. Okay, and so that shows everything there is to discuss regarding equivalence of these two particular linear programs, and all the techniques that we used here were more or less generalizable. So this applies in general to whenever you want to reformulate linear programs. So that's really it for this video then. Linear programs really are equivalent, and this is what we meant by it. So we can move on to further topics in duality from now on. Okay, so that's it. Thanks for watching.